of the four properties. Remember the activity we did on the first class, where we basically started talking about the four different kind of properties we're going to study in this course. Remember, electrical, magnetic, optical, and thermal properties. So the idea is you're going to choose any object. Okay, so it's kind of the dynamic with it, but now it's obviously with certain, let's say, probably I would say an in-depth explanation, right? So the idea here is you'll have to choose a material, a property, and then explain, why did people come up with this material. I'm going to encourage you, try to look for a new material, for an interesting application that it fits inside any of these four fields. And so how did the creator sort of address the problem, or is trying to address the problem, right? Because the idea of developing new materials or trying to use materials for new applications is actually trying to address a problem. So try to focus on that. So the idea of this coffee break is choosing a new material or a material for a new application. And that application has to be related to any of the four main properties we will talk about in the course. And then address mention how are they addressing the problem? How are they trying to solve the issue? And how is this new material or this material will help for that? Okay, so you will be the first to present. Please, 5 to 7 minutes, not longer than that. Okay, okay, that's it. Everyone else, please also turn your cameras on. And if I highly recommend you to be on a computer, because we will use whiteboard. And obviously, I think it's a lot more difficult to use it on a cell phone, right? So please get a computer if you're connected on a cell phone. Okay, I'm just gonna do a brief review of the slides I uploaded, because where is it? This should be. Well, this is just basically sort of let me check, where is it? Okay. Oops. Okay, this is just a quick review. Okay, not really of what we saw on Monday, but just of certain things that will be useful, right? And in terms of mathematics. So this slide you have it in the slide set that I presented on Monday. So these are a few of the main equations we'll use. Plus, I'm gonna write actually some of the other ones that, remember, I said I forgot certain ones. So I'm gonna actually write them right now. Let me see, where is it? Okay, let's use red, I think. Okay. So what equation is missing here, or what equations actually? I already mentioned this on Monday, but I'm just writing it again. Remember that simple equation: the reduced Planck's constant is equal to the Planck's constant divided by 2 pi. We'll definitely use that. We'll also use this. Okay, this equation is going to be very useful. Let me see what other equation did I miss. Oh yeah, I missed this equation, I think. Remember, this is angular frequency is equal to 2 times pi times. Remember, this is frequency, right? This is not really velocity. Velocity is, I don't think we have, yeah, I think we have velocity here. That is velocity, okay? In the momentum equation, momentum is equal to mass times velocity. So that v is not equal to this v, right? Remember, this v is frequency of the light wave. It's the same v we have here in angular frequency, right? That's not velocity. Velocity is this v, the v from momentum, okay? I forgot this equation. Remember that the wavelength times the momentum is equal to the Planck's constant. What else did I miss? I think that's pretty much it, because we have everything else here, or at least I mentioned most of it. I'm just gonna recall also the wave number. Remember, the wave number is equal to the inverse of the wavelength times 2 pi. Okay, remember that this is actually a vector, should be called the wave vector, but for simplicity, we define it as the wave number. So the wave number is the inverse of the wavelength times 2 pi. And I think that's pretty much it. I think we can come up with the rest of equations just with these ones. Then we can just replace everything else and then come up with other equations. Yeah, I think that's it. Okay. Wait, actually, I might be missing. Yeah, I'm actually missing this equation as well. The energy is equal to the velocity. Sorry, that's frequency actually times Planck's constant. The frequency of the light wave times the Planck's constant. That's also an equation I was missing. I'm sorry. So all the equations that are there plus the ones I wrote now, I think those will be the basis, at least for this first module. We'll need most of them, or if not all of them. Okay, so just remember that. Who recognizes what these equations are? Anyone? Well, you'll need this as well.
Euler's identity.
Yes, all of these are Euler's equations, and you'll definitely need this. Okay, so that's why I put it there also, so you can have them at hand. We'll need Euler's equations as well, so please keep them in your mind and keep them at hand. Okay, time to work, and let's actually derive this equation. In class, we saw that the time-dependent Schrodinger equation is this one, but we didn't actually see how is it that this equation appears, and that's what we're gonna do now. Okay, so I'm gonna stop sharing this, and it's time to go to whiteboard. And now everyone is gonna work. Okay, let me see. Hopefully it's gonna work. Okay. Let's actually do this, okay? And for that, I will, okay, I'm just gonna go and ask people to participate, I guess. And I'm gonna start with the easy thing, and then, you know, the idea is to derive this, well, not derive the equation, but see, you know, how it appears and why is it that the final form of the equation is that. So if you remember, and I'm just going to start with this and then you all will continue, okay? If you remember, we saw that the wave function, right? If we're talking about time dependency, and let's say we're talking, well, whatever, if it's in one dimension, it will depend only on x. If it's 3 dimensions, it will depend on x, y, z. And obviously, if it's a time-dependent equation, it depends on time, right? So we saw that, we all know that, okay, easy. And we also saw, and it's obvious that this will be, right, same Schrodinger equation independent of time. So times this term, right? E to the I times the angular frequency times time, and this becomes the time component, right? That's the small change. That's it. Okay, guys, please don't edit yet. Okay. So that's the first part. That's the easy part. That's the obvious part. All what I did is just separate, and this should be equal. Okay, sorry. The Schrodinger equation, the time-dependent Schrodinger equation, it should be a product of the independent, time-independent Schrodinger equation times a time component, which, you know, by definition we could derive that, but we're not going to do that in this class, in this course, times this term that becomes the time-dependent term. Okay, so from here we're gonna continue, and I'm just gonna go with the order in my screen. Okay, so as I have them on my screen, we will go one by one. So Fernando, you're the first on my screen. Let's take the derivative of this with respect to time. So let's differentiate this with respect to time. And I want to see you doing it here in the whiteboard. Go ahead, please. Let me just do it smaller because I don't really see. Sorry. Let me use the drag. Okay. So the differential, it's equal to the function times IWE IWT. Okay, that's great. Perfect. Let's go with Julio. You're the next. Oh, sorry, guys. You're the next one. So, if you realize, or anyone, if you guys realize, we have something here. There should be a product here, right? So we have product of, okay. We can see something here, Julio. Can you replace that? Can you rewrite this? Or anyone?
It will be the original function.
Yes, Fernando, but let's wait for someone else. Yeah. So yeah, just I think, yeah, I mean, I think you got the idea, and it's great, but I will use the other symbol, because remember, this is capital, right? This is just so I think you got the point, but this actually will be better if we use the right notation, which will be this one, right? The capital letter, because that will mean what you're using here, right? Depends on x and t. So we use the capital letter times I and times w. Okay, we're perfect, and I'm just gonna rewrite this because I guess it's just better. Okay, the differential of the y function with respect to time. Okay, guys. Who's next on my screen? Jose. What will you do next? The idea is to basically get the final form. The form that is in the slide. We need to get there, right? And all we're doing is just trying to rearrange this equation so we can actually solve it later. And obviously the first step was differentiating with respect to time, which is great. And now, what will you do? Remember that here you have a term that eventually will be quite useful because we can replace this term. When you're seeing this, remember in that equation, there's a term that you can replace it eventually. So you can rearrange for that term. Just rearrange the equation for that term. A term that eventually will be quite useful. Remember that this, I guess I'm gonna give you the best hint. Remember that all of this, in the first class, everything was about the energy. All we were trying to get was energy. Because remember, all we're talking about here is energy, and then eventually we got energy levels. But everything is about energy and energy distribution and energy levels. So the idea of any of these Schrodinger equations is to put them in terms of energy. And there is a term here that you can relate to energy. So let's solve for that term, and then we can see how we can rearrange this equation. What is that term? And please rearrange it. Remember, the key part here is everything is energy. And everything that we'll actually talk in the whole course will be about energy. So the idea is always try to get something towards energy.
Can I derive the function for second time?
Okay, if you take the derivative of the second derivative, what will you get? What will be the benefit of that? Again, you can isolate for a term.
Maybe we can replace the frequency, the angular frequency.
Yes. So, and that's okay, Miguel. So that's the key term here. When we see this equation, this part, the key term here that eventually we can relate to energy is angular frequency. Okay, so Miguel, now, Jose, it will be your turn later. Miguel, please isolate for the angular frequency, and then we can see how can we replace it, okay? But do the first step now. Please.
You mean isolating by just...
Yeah, isolate means you just say angular frequency equal this. That's isolation.
Okay. Wait. With
okay.
Like
yes.
and then
yes.
we relate W with the the function dependent on the position.
Okay, yes, that's great. Give me 1 second because I just want to see things easier. Okay, and I want to make people to see things a bit easier. But yes, you got the idea, and it'll be your turn. Just give me 1 second. I just need to sort of move this a bit, drag it here, and rearrange this a bit. It's the same thing you did, just that I guess I just like the full notation because it's just easier for me to visualize that. So it will be d with respect to time will be times 1 over I times the function, and that is equal to w, right? So it's the same thing you wrote. I'm just rewriting it just to make things easier. Now, here we have one term before we jump into the next thing. I guess I can replace this with what? Can anyone tell me? One over I. How can you replace that?
With it hyperbolic sign. I don't know if that's the pronunciation.
Not really. Remember, 1 over I is equal to negative I, right? Am I wrong? Am I crazy? I think it's correct, right? 1 over I is equal to negative I. Yeah, you can do the conjugate.
The conjugate number.
Sorry?
The conjugate.
Yeah. So it will be just negative I. Okay. So let me. I mean, you can do that, I guess, on your own notebook, but you can see that I'm right. That I'm not inventing something, or I'm just not coming up with crazy, stupid ideas, right? So I'm just gonna rewrite this. I'm doing this because, to me at least, this just makes things easier, because this will be a huge equation eventually, and I guess for me it's just easier. So I'm just gonna rewrite this, okay? So it will be W, the angular frequency, omega, it's not W, it's equal to negative I over the wave function times the derivative of the wave function with respect to time. Okay, so I think this is I, it's not 1, just to make things clear. Okay, now Miguel, you were saying something. We can replace angular frequency with something. With what?
Angular frequency is equal to 2 pi the frequency, and we can use that into the
Okay, write it.
energy equation. I don't know if that is correct.
Use the whiteboard and explain us, please.
Okay.
Remember, all we're trying to do at the end, and we should always do that, is relate any Schrodinger equation, or just put any Schrodinger equation in terms of energy, because that's all what we were studying. Everything is energy. Everything is energy. Okay.
I don't know if replacing that has a. I mean, there must be a connection with the function, but dependent on the position of the particle.
Okay.
I don't know how to get there.
Okay, no, it's great. It's great. Don't worry, it's great. I mean, you got the idea with what's, I guess, the best thing here. Now we need to find something. So Miguel wrote two equations there. Remember that the F he wrote, it's frequency that for us, at least in the equations I showed you, frequency to me is, it's this, right? It's like this B, right? That's frequency. Remember, that's the one I'm using for frequency. Okay. Miguel, is you writing or who's writing now?
Me, but
I'm writing
yeah,
on
I
a,
was.
Sorry?
I'm writing on a side. I saw those two equations, and I think they may relate through that V.
Okay. Let's keep those equations there. I'm gonna go with the next person. Let's actually go with Joshua. Joshua. The idea and what we did before is isolating for the angular frequency, right? The idea is to basically find something that can relate or that allows me to relate the angular frequency to energy. There are a bunch of equations there written by your classmates. What will you use? Either the ones you that are there, you can use one that I wrote, at the beginning of the class. You might do a combination, but the idea is to get the angular frequency in terms of energy. You can use the whiteboard. That's the idea, right? Let me just drag and zoom out because now I have a lot of things here. Oops, sorry. Oops, okay, now you can use the whiteboard. That's the idea, right? The idea is we all should see this and collaborate on this.
Could I use the constant Planck, this equation of wavelength times the momentum equals to constant Planck?
You can use any equation as long as at the end I can see a relation between angular frequency and energy.
What about that?
Okay, well, first of all, I don't really understand what you wrote. Can you just
I
explain?
I replaced the velocity with the
Okay, sorry. Let's go one by one. I'm gonna choose another color. Okay, because I don't quite understand. So this is the angular frequency. It
yes,
says equal to 2 times pi times what? Is this velocity?
velocity, yes.
Okay,
Velocity,
velocity. Okay, so you replace frequency with this equation, with velocity and the wavelength.
yes.
Okay, from here, what did you do?
Now I take away velocity and made this,
Did you jump from here to this one?
yes,
Okay, so it says you isolate for velocity. So velocity is equal to angular frequency times wavelength
length,
over 2 pi.
yes.
Okay, so this is, okay, so you just isolated for velocity here. Okay,
Now I replace it in the equation of the energy.
okay, equation of energy, which equation? Energy is equal to a half times
Half
mass times
mass
velocity.
velocity square.
Okay, so energy is equal to 1/8 of pi square. Yeah, and W. Yeah, what is this? Is this times? What's that?
The mass, the mass, m.
Oh, whoa. Okay, 1/8 of mass times. Okay. Yeah, it works, I guess. I mean, it's a smart way, quite a long way though. Then we'll have to isolate for the angular frequency because that's what we need. But it will be, I think it'll be quite long. And then, okay, let's actually simplify this. Let's make things easier, guys. Okay. With just two equations I gave you, you can do this a lot easier, right? Remember this equation, energy is equal to frequency times the Planck's constant. I wrote that equation. I don't think it's in the, is it? Might be, I'm not sure. I'm not sure if it's in the slide, but I wrote it. Okay. So energy is equal to the Planck's constant times frequency. That's easy, right? And I wrote that equation. Now I'm gonna use the one you use here. Okay, now I'm gonna use this one. So if I isolate for, I'm sorry, this is a mess now, but anyways, so if I use this, I know that, sorry, frequency is equal to the angular frequency divided by 2 pi. Do we all agree on that? Right? Okay, so I'm gonna say that's equal to the angular frequency over 2 pi. And we're all on the same page. Times the Planck's constant, right? But remember that the Planck's constant is equal to, and I can write this again, W over 2 pi, sorry, angular frequency times 2 pi. Remember that the that the Planck's constant is equal to what? To the reduced Planck's constant times 2 pi, right? Therefore, bye-bye 2 pi's, the energy is equal to the angular frequency times the reduced Planck's constant. As easy as that. Okay. Therefore, oops, sorry. Okay. Therefore, I'm just gonna use yellow now. No, sorry, I'm gonna use this now. Actually, let me highlight. So E, well, oops, sorry. Let me hopefully erase this. Let me use again. This will be E. Therefore, I'm just gonna use this equation, and I know that the angular frequency is equal to the energy divided by the reduced Planck's constant. And therefore, now I can use this equation, right? I'm going to call this equation A. And I can use it now with equation B. This is equation B, right? Therefore, if I combine these two equations, what will I get? Well, I'm going to get energy divided by the reduced Planck's constant, that's W, right? It's equal to negative I over the wave function times the derivative of the wave function with respect to time. I think that's easy. I can obviously solve for energy here, and I can say energy is equal to minus a reduced Planck's constant over the wave function times the derivative of the wave function with respect to time. And now we have an equation for energy and the wave function. Is it clear, guys, so far? Yes. No.
Yes.
Okay. Now, how do I move on? Who has an idea? I have this. Now, what do I do? What's the whole point of getting energy? So I did all this work to relate the energy to the wave function, obviously. That's great, amazing. I did it, great. Now, what do I do with this energy? Remember, Schrödinger equation, all about energy. What do I do?
Add it to
Add it
the
to
other terms of the equation. Yes.
add it to the other terms of the equation.
So we will. Yes.
So you mean what? I think you got the idea. No, I think you got the idea.
The thing is, I think that I don't know. The thing is that we don't have the mass, so we will have to relate it to the alpha. No.
I mean, everyone knows what the mass of an electron is. You can Google that. That's quite easy.
No. I mean that in the final equation, in the time dependent, there is the mass term. So that's missing, and the mass is in the alpha term. So maybe we can use alpha to complete the equation, or I don't know.
Okay. That's a good idea, but you haven't answered my question. My question. What am I doing with this? What can I do with this equation of energy? It's quite easy, guys. Just only one step. And we can get we're not going to solve the Schrödinger equation yet, right? We're not going to solve it. We're now trying to work with energy, and eventually my final result is I want to demonstrate how can I get the equation you have in the slide. How do I get that equation? Because that's the one to solve. Yes, then we can solve that. We're not going to do that today. We can eventually solve that for sure. But the idea, again, is how do I get that equation that you see in the slide? And to get that equation, I need to relate the energy to the wave function. Okay, I did that. I related energy to the wave function. Great. So now what's the next step?
No, derivate again.
Sorry?
Derivate again.
Okay, what?
Yeah, the
Energy.
main function.
Yeah, but for what? With respect to what? No.
To time. In order to get the second derivative.
So you want me to take the derivative of what? Of this equation with respect to time?
Yeah, the last one, I guess.
Okay, let's just think, guys. I already have energy here related to the wave function. I got what I needed. I already got what I needed. Really, the next step is quite simple. I cannot change the Schrodinger equation because the Schrodinger equation is there. I mean, we can derive the Schrodinger equation if you want to. That is, 5 pages notebook derivation with a lot of things, but that's for mathematicians. We know that the Schrodinger equation has this shape, right? We all know that the Schrodinger equation is that, or actually, sorry, let me just, well, I mean, I guess it depends how you're considering it. If you're considering with time or no, let's consider the independent one. So we all know this. I mean, this is something that is given that, again, you can easily derive, right? But, well, not easily. It will take a long time, but you can derive if you wish. But this is the general shape of the Schrodinger equation, right? That we saw that's the case. And again, you can derive that if you wish on your own time. I don't think that matters for this course, to be honest, because we'll take it as given, okay? So what's the point? Why did I do all this? Because I don't know what the energy is. Well, at least I didn't know what the energy is here. And that's the whole point of getting to this. It's really because I needed to know what this energy term is. Because if I'm talking about a case where, it's a time dependent case, I don't know what the energy looks like. I have no idea what that energy is like. Therefore, I don't want to solve the Schrodinger equation yet. So I don't need to solve this yet. All what I needed to do, and that was the whole point, is just replacing this so I can understand, well, with respect to time now, so this actually should be the wave function with respect to time plus 2m over h squared. Actually, let's, because I'm gonna just write it. So it will be 2m over reduced Planck's constant squared times e. But remember, e is all this term, right? So this actually will be negative because I have plus times minus will be 2m over reduced Planck's constant, not the square, because it will cancel out with the energy term, right? And that will be negative 2mi over h times the derivative of the wave function with respect to time, and negative as well. That will be what? 2m over reduced Planck's constant squared times v and times the wave function. Okay, so all I did is just replacing e with this form I got here, right? You can replace in this general, because that's the general Schrodinger's equation, you just replace for energy in that equation and you will get this. Okay, And that's actually the equation that if we were to solve it, we need to solve this equation. Okay. We can't solve this equation above because that's too general. Okay. The equation we have to solve, if we were to solve it now, it's this one. This is actually the important one now. Okay. So, and this is how we get, if you see, this is the same equation that is presented in the slides. And again, all I did is just replacing in the general Schrodinger's equation, I just replaced with energy, and you can do it step by step. You will get the same result, I'm sure. Oh, sorry, this actually should be a minus, shouldn't it? Because it's negative. Yeah.
No, it's supposed to be a plus. I already checked.
No, why it should be a plus? Should be because it's plus times negative I. You get a negative here, and then here you get plus times negative potential. So yeah, it should be a negative. In the equation I gave you, it should be, yeah, negative and negative. Yeah, because it's plus here, the 2m, times E, but E is negative because you have remember that we got negative I, right? So plus times minus is minus, and here also should be a minus because it's plus times minus, because B, it's minus the potential, right? The potential energy. So plus times minus is minus. Yeah, it should be 2 negatives. Yeah, that should be right. And you can compare this, and again, you can do it step by step if you wish, and you can compare this to the equation you have in the slides. But in the slides, yeah, it's two negative signs, which makes sense. And this is equal to 0, right? I'm sorry, I forgot to. This is equal to 0, and then we can solve that equation. But that's not gonna be for this module. We'll do a case, I think module 2 or 3, where we'll need to solve this equation. Questions, guys? Is it clear? This is just mathematics, right? It's not really there. But that's what the tutorials are meant to be. It's just trying to relate a bit of concepts of the class to the mathematics part, which I know it's a bit hard, or might be hard if you don't really remember how to do this. But at the end, you see it's just replacing equations, and we just had to take one derivative, easy derivative, and then everything else was just replacing equations and thinking how to relate energy to the wave function. Is it clear, guys? Okay. Before we finish the class, I will actually like to start with the next case. So if you go to your slides, if you see the last slide of this set of slides, you will see there's another case that we didn't see in class, because remember we saw the free energy case, we saw the electron potential barrier. Remember we had an electron in a well, basically, that was traveling back and forth within that well. And then we have this last case that is the tunnel effect. Okay, you can see your slides. And this case is quite interesting, right? Because we have a case, and I'm just gonna redraw it, I guess, here. It's something like this, right? Where we have the energy, and we have, well, the potential energy, and we have X. And what it's saying, it's, let's do a case where I have this, right? Basically, it means the electron is traveling, right? It's traveling free and nicely. Let me use this color. The electron is traveling free and nicely. Okay, it looks like a free electron, but then boom, it finds this wall. it crashes the wall, right? By the way, this wall is supposed to have a finite electron potential energy. Sorry, we call it B naught. That's the potential energy of the barrier. And by the way, this barrier, we're just gonna set that condition. This barrier should be greater than the total energy of the system. So the electron is traveling, right? It's traveling freely, coming in the positive X direction, and boom, it finds the wall, it finds this potential barrier. And then, you know, it has to sort of overcome this barrier, and then it can keep traveling. So it has to sort of come over here, but you know that this fact here, right here, something's happening, right? Because it's not as easy as just penetrating that barrier, but it will have to do it, and then it can keep coming and coming and coming, right? So this is called a tunnel effect. Let's basically think of this wall, of this potential barrier that we have here. Let's think of this as a tunnel, right? That the electron is sort of passing through it, but it's not as easy as moving, as if it would be moving in just like a free potential space. Okay, so if we're talking about this case, and if we're thinking on coming up with an equation that describes this movement, for this case, such as we did for the free electrons, such as we did with the potential well, we need to come up with equations that describe this behavior, right? How are we gonna do that? Well, we can, I guess the easiest thing we can do is divide this into two regions, because there are two different behaviors here. I have a completely different behavior in region 1, which is just before this potential barrier I have, and then I have region 2 after this potential barrier. So basically the potential barrier becomes a big wall there that's dividing the movement of the electron into two regions. And now I need equations that can describe the movement of an electron in each of these regions. And we're gonna finish. I just need someone that can tell me how or what equation will you use to describe the behavior of the electron in region number 1. And actually that someone is gonna be someone that hasn't participated. So Jose, what equation will you use for the first region? How will you describe the movement of the electron in this region, in the first region?
The first equation.
Sorry?
The first equation, Schrödinger equation, that time independent, or no?
Yeah, okay, time independent, but can you write the equation if you have it at hand? How? Okay, okay. Yeah, so it's Schrodinger's equation. I guess it should be just the lowercase one because it's not really depending on time, but okay, continue please. Yes, That's correct. Again, I will just replace. That's perfect. Thanks, Jose. I will just replace this one. I'm just going to use this one. This one with the lowercase, right? Because it's not really depending on time. So this will be just the lowercase. And remember, this is the reduced Planck's constant. It's not the Planck's constant. It's the reduced one. What's the point here? And all what you did, Jose? It's here. This, if we come back up, let me find it. Yeah, this general equation, right? In this general equation, all Jose did, and this is the free electron case, the potential energy becomes zero. So that's why the equation just becomes E, the energy times the wave function. Because we're talking here, in this region, in region 1, the electron is moving freely. There's nothing happening. The electron is just, as in the free energy case, in the free electron case, the electron is just moving with no barrier. Therefore, the equation that describes the behavior of the electron in that region is the same we use for the electron, for the free electron case, where the potential energy is zero, because I have no electron, I have no potential energy in that region. Okay, that's it. Thanks, guys. Thank you for joining. We'll continue this in the next tutorial. Have an excellent night. And for those that want to talk about the paper, you guys can remain and we can talk about that. Thanks, guys, and have a wonderful night.
Thanks. See you later.